exercise questions. Okay, Bismillahirrahmanirrahim and good morning. So I would just like to recap this part on aqueous silver nitrate because I think last lesson I was rushing through this section. So when you react halogenoalkanes with aqueous silver nitrate, there are two reactions happening. Okay, the first one is the nucleophilic substitution with water. That water comes from the aqueous part of the silver nitrate. Okay, so what happens is that water will substitute whatever halogen you have in the halogenoalkane. The halogen will leave as a leaving group to become a halide. So whether it's chloride, bromide, or iodide. After that, the second reaction is then with the silver nitrate, more specifically the silver ions. So this reaction is called the precipitation reaction. Silver ions is actually a test for halides. If you remember from your qualitative analysis notes, silver ions are used to test for your halides as they produce precipitate, and different color precipitate represent different halides present. Okay. So then the second reaction is the precipitation reaction. It is usually shown as an ionic equation. The nitrate ions are just floating in the reaction mixture, so we don't usually show it in the equation. So iodide will react with silver ions to form a silver halide. So this can be silver iodide, silver chloride, or silver bromide. Again, they will have its own characteristic colors. Okay. So with that said, aqueous silver nitrate is a reagent, the reagent used to test for halogenoalkanes. And it's also used to study the rate of hydrolysis. Okay, because we can see precipitate, we can record the time taken for the precipitate to be formed. And from there, we can study about the rate of hydrolysis. Okay, this part, the fastest nucleophilic substitution reactions would take place with iodoalkanes because the carbon iodine bond is the weakest bond, therefore it will be the one that is broken first. The slowest nucleophilic substitution will happen with fluoroalkanes because the carbon fluorine bond is very strong. Therefore, it will take a while for hydrolysis to for the bonds to be broken. Okay, it may or may not be broken, right? But for your syllabus, you will look at chlorine, bromine, and iodine, not so much for fluoroalkane. Okay, cannot spell fluoroalkanes. Right. So that's done. Okay. Just to summarize, with that said, your iodoalkanes are the most reactive halogenoalkanes, and your fluoroalkanes are the least reactive, right? So next we move on to the last section of this topic, which is elimination reactions. So elimination reaction is when you use sodium hydroxide in ethanol. Now, if you remember, there is one reaction of halogenoalkanes with sodium hydroxide as well, but this one is called a nucleophilic substitution. Okay, so substitution reaction with sodium hydroxide is when you use aqueous as your solvent. Right? So the solvent is very important. If you just write down sodium hydroxide on its own, you will be penalized. Okay, so please do not forget, especially for halogenoalkanes. For other functional groups, it's fine. If you just write down bromine Br2 without the aqueous for alkenes, that is fine. Okay, but for halogenoalkanes, especially the sodium hydroxide, it is extremely important because different solvent will result in different reaction. So when you use aqueous sodium hydroxide, you get a substitution reaction. So that's either your SN1 or SN2. For alcoholic sodium hydroxide, for example, like you use ethanol to dissolve your sodium hydroxide, elimination reaction will happen. Okay, so you can copy this example just above the elimination of 2-bromopropane. Okay, so we'll have a look at 2-bromopropane later on. So this is just an example of the elimination reaction of bromoethane when you react it with alcoholic sodium hydroxide. So in this case, the molecule that is being eliminated is your HBr. Okay, so that means if I just number my carbon and I know I need to remove bromine, and bromine is sitting on carbon number 2, that means my hydrogen has to come from carbon number 1, whether it's this one or this or this one. It doesn't matter as long as it is not the hydrogen from carbon number 2. Okay, so I'm just going to choose this one, right? If you are not able to see it clearly, like where bromine is from and then who is the neighboring carbon, number your carbon. Okay, number them. If carbon is already sitting on, if bromine is already sitting on carbon number 2, that means you cannot remove anything else from carbon number 2. Okay, so what happens is that if you imagine you lose the bromine from carbon number 2 and you lose the hydrogen from carbon number 1, if you notice that now each carbon only has 3 bonds and they need 4 bonds. The 4th bond is the double bond being formed between the carbon-carbon atom. Okay, so this is the case where you turn your halogenoalkanes to become an alkene in an elimination reaction. Okay, so elimination is removal of small molecules from the organic molecule. So often water, but in this case it would be hydrogen halide. It's HBr, HCl, or HI. Okay, the condition is you heat it under reflux, so that's quite standard as well. The new functional group that you form is ethene. So you go from a bromoethane to an ethene. Sorry, bromoethane to an ethene. And then, as mentioned, you lose H+, you lose Br-. The hydroxide ions comes from the NaOH, and then the Na+ also comes from NaOH. And when they combine, they become NaBr plus water. Okay, so the hydroxide ions from the sodium hydroxide combines with the hydrogen you have lost from the halogenoalkane, and then the sodium from the sodium hydroxide will combine with the bromine atom that you lost from your halogenoalkane. Okay, so if I just highlight that HBr in yellow, that means it came from the bromoethane, right? So to write it in equation, this is how you would do it. Okay, C2H5Br plus NaOH in ethanol. You heat it under reflux. You get an ethene, sodium bromide, and water. Okay, now, so I want you to add an extra note. Hydrogen, and halogen are removed from adjacent or neighboring carbon. Okay, so sorry, this is extremely important. Okay, and where you draw your double bond, of course, has to be from the same carbon that you have lost the atoms. Okay, in this case, there are only 2 carbons, so you don't really have a lot of choice. But when you have a much more complicated and bigger molecules, it's easy to lose track of where the double bond should go. Okay, so it's advisable for you to always number your carbon atoms so that you know, oh, I've lost an atom, a hydrogen atom from carbon 1, a bromine atom from carbon 2. So my double bond must be between carbon 1 and carbon 2. Okay. Right, so can you please copy this down? When you're done, please let me know so that we can move on to the examples. Okay, the next one is elimination of 2-bromopropane.
Miss,
Yes.
for the NaOH, is it important that we have to put in the ethanol?
Yes, because if it is aqueous, then it undergoes the substitution reaction.
Okay,
And
you.
if you just write it down as NaOH, then that is ambiguous, so your answer will not be accepted. Okay.
Okay.
Are you done? Okay. Right, thank you. Moving on to the example, elimination of 2-bromopropane. So this is straightforward, okay? So propane, and there is a bromine on the second carbon. 1, 2, 3, okay? And the rest of the molecules is just your hydrogen. So during an elimination reaction, you will most importantly lose the bromine first. Okay, so bromine is on carbon number 2. So now you have a choice between carbon number 1 and carbon number 3. Okay, so but in this case, carbon number 1 and carbon number 3 is actually the same. Okay, so I'm just going to lose the hydrogen from carbon number 1. That means if I react it with hydroxide ion in ethanol, okay, you can write it down as ETH, no problem, ethanol. And then this undergoes, you treat it with heat under reflux. So then you would have lost 1 bond from each carbon 1 and carbon 2. Okay, so in order to make carbon 1 and carbon 2 to have 4 bonds, you need to form a double bond. Okay, you can try for the other one. When you lose bromine from carbon 2 and hydrogen from carbon number 3, if you just flip the molecule, it will be exactly the same. Okay, so only one single product is formed here. Other products would be bromide ion plus H2O. Okay. And then the last one, the last example would be your 2-chloro 2-methyl butane. Please let me know when you are done copying this down. Okay, thank you. 2-chloro-2-methylbutane. Okay, so let's draw. Butane has 4 carbons, 2-chloro and 2-methyl. Okay, or you can draw out the CH3, no problem. I would number the carbons 1, 2, 3, 4. Okay, so I will lose my chlorine from carbon number 2. So I now have a choice to lose hydrogen from carbon 1 or hydrogen from carbon 3. As a matter of fact, I can have 2 products. I will form 2 products actually, right? So the first one is when we lose when we lose hydrogen from carbon 1 and the chlorine from carbon 2, that means I end up with this. So I'll just leave the CH3 as it is. So that's 1, 2, 3, 4. Carbon number 3 and carbon number 4 are not affected. So I just continue to draw the hydrogen as it is. So you notice that I've lost 1 bond from carbon 1 and 1 bond from carbon 2. That means my double bond has to be from carbon 1 and carbon 2. Okay. What if I lose the chlorine from carbon number 2? That one I don't have any other choice. I have to lose that chlorine, and I lose the hydrogen from carbon number 3. So I will now get another product, a different product. Carbon 1, carbon 2, carbon 3, carbon 4. Okay, so carbon 1 stays unchanged. Carbon 2, I have lost the chlorine. Carbon 3, I have lost 1 hydrogen. Carbon 4 stays unchanged. So you can see that I've lost the bonds here. My double bond has to be formed between carbon 2 and carbon 3. And are they different? Yes, they are different because the position of the double bond is different. So when we name this, the bottom molecule is called a 2-methyl but2-in, and the top molecule is called 2-methyl but1-in. Okay, plus other stuff, as you all know, plus H2O and Br minus. Okay, so I forgot to add on OH minus ethanol. Okay, and then this one will also form H2O plus Br minus. Okay, so with unsymmetrical secondary and tertiary halogenoalkanes, sometimes 2 or even 3 products can be formed. Okay, so it depends on the starting material. Now, I've had students asking me, what about if we lose hydrogen from this carbon? Because this is a different carbon to carbon number 2, right? So we can still lose hydrogens from this carbon because it is adjacent to carbon number 2. Well, you will just be forming the same product anyway. Okay, so this carbon number 2 has the option to lose from carbon 1 or this side chain carbon. It's the same thing. It will give you the same product. Okay. Okay, any questions before you go?